Here we are, part B. F of xy equals 2y to the third plus 6xy minus x squared. Okay, well, we're going to go through the same steps, of course, but it's going to be a little bit more difficult the way this plays out. And we can see even the nature of the function looks a bit more complex. So let's start it off. We need the two first derivatives with respect to x and with respect to y. So I've got those right here. Let's talk about those. If we take the derivative with respect to x, well, that means y is a constant. So this whole part here goes to 0. This part, well, if y is a constant, then it's like constant x. Now 6 times some other number times x. If I take that derivative, the derivative of x is 1, so I just get the constant 6y. And finally, the derivative of minus x squared, well, that's normal, minus 2x. Okay, the derivative with respect to y. Well, 2y to the third is 6y squared. But then something similar happens in the middle, 6xy. The x is constant, the derivative of y is 1, so that constant multiple just carries down, 6x, and the derivative of the x squared is 0. All right, so now that we have fx and fy, say, okay, both of them involve x and y, right? So we need to set them both equal to 0. And 6y minus 2x equals 0. 6y squared plus 6x equals 0. Let's simplify those both, because I noticed there's some common factors. So if I divide this derivative, everything by 2, if I divide here by 6, I can make that look a little bit simpler. All right, what are we going to do with this? So you notice that we can't just solve for x and solve for y as simply as we could back in part A. What's going to happen? We need to think of this like a system of equations, right? We've got our two equations and two variables. So there might be more than one combination of x's and y's that will make both of these derivatives equal 0. We need to find all xy where both are true. Okay, how are we going to do that? Well, if it's a system of equations, then a good technique is to use substitution. You guys remember substitution from solving systems? And that's going to be a really good method here. What I'm going to do is isolate the x. I'm just going to add the x over. And I think I'll just show you kind of most of my work as I'm going, but I'm going to start here in this left column. So I'm going to begin with that simpler one. I'm going to add the x over and get x equals 3y. All right. Then I'm going to take that 3y and I'm going to substitute it back over here in this x. Y squared plus 3y equals 0. And now I can solve for y. I need to factor. All right, y times y plus 3, and I get two values of y, 0, and from this one, negative 3. Okay, since I have two y values, I want to find the x value that goes with each. So I'll start with y equals 0. And I'm just going to plug it in right here to get the corresponding x value. Well, x would equal 0 as well. So one of my critical points is 0, 0. I'll take y equals negative 3, and I'll plug that in. And the x value that goes with that y value is negative 9. So another critical number, critical value, critical point, which whatever it is, negative 9, negative 3. Now it's probably a good idea. We've solved the system here. Just go back and confirm that both of these points really do make each of those first derivatives equal to 0. So if I took both x and y as zeros and I put it back here, x is 0, y is 0, well, I'd get 0 there, and I would get 0 here. And if I took these numbers for x and y and put them back in, both of these would be 0 as well. So I won't talk about those. I won't like crunch the numbers for you, but if we plugged, the 0, 0 is pretty clear, but if we plugged x equals -9 and y equals -3 into each of these, we'd get zeros for both of them as well. Not a bad idea to check before you go any further. Okay, what does this mean? So if we have two critical numbers, then we're going to need to find the values of a, b, and c for each one of them. A, b, and c for this one, a, b, and c for this one. And of course, first we need those second derivatives, so maybe we go there next. Here are the second derivatives, and I don't think I'm going to be able to fit it all on the screen at once. But if you look back at fx and take another derivative with respect to x, then you'll get -2. If you look at fx and take the derivative with respect to y, you'll get 6. And if you look at fy and take the derivative with respect to y, you get 12y. And notice finally we got a second derivative that was not just a constant. These two did end up being constant. It's pretty typical that your second derivatives in the problems we're going to see end up being constant. But hey, we got something that's not, so that's a little different. Okay, let's begin with 0, 0. Let's find the values of a, b, and c based on these second derivatives. So what does that mean? So we take x equals 0, y equals 0, and plug them in here. Well, there's no value of x or y, so we just get the -2. That's our a. B, we look at this one, plug in 0, 0. Well, it's just going to give us 6. But c, 0, 0, well, the y is 0, so 12 times 0. And there you go, -2, 6, and 0. Okay, so AC minus B squared, that gives us -36. What does that mean? Oh, looks like I'm at the bottom of this page. If AC minus B squared is negative, well, you guys know that gives us the saddle point. We know there is a saddle point at the origin. Well, actually we don't know it's the origin, but it's at 0, 0. We don't know what the z value is. We haven't done it yet, I should say. Okay, so saddle point at 0, 0. Now we need to do the same thing for the other critical number, -9, -3. So we will plug in -9, -3 into that fxx. Of course, that's just going to give us -2. We'll plug it into fxy. Well, that's just going to be 6. But fxy, we're able to plug in the y equals -3. 12 times -3 gives us the -36. All right, and then of course once again we look at AC minus B squared, -2 times -36 minus 6 squared. And it turns out this one is positive 36. Okay, if we get a positive for AC minus B squared, then remember we need to look back at the value of A. The value of A is going to tell us if it's a max or a min. Well, A, so this part was positive. A, we can see, is negative. So if that part gives us a positive, we know both derivatives are going in the same direction. If this is negative, we know it's concave down. And so we have a local max. I see I have a mistake here. That should have been YY, not XY. My mistake. Sorry if that confused you. This was positive, this was negative. There's a local max at -9, -3. Okay, to wrap up the question, we need to know the z values for each of our critical points before we state the final answer. So here I'm calculating those. Going back to the original function at 0, 0, zeros for both x and y, well, of course we get 0. Hey, it really is the origin. And at the point -9, -3, seems a little weird. Okay, so there was 2y to the third plus 6xy minus x squared. Okay, so there you have it right there. 2 times -3 to the third plus 6 times -9 times -3 minus -9 squared. You'll get 27. And so we know there is a saddle point at 0, 0, 0. And there's a local max at -9, -3, 27. I invite you guys, go check it out. In GeoGebra, the trickiest part about GeoGebra is the zooming. So kind of play with it, get used to it. All you need to do is plot the original function, f of xy, usually call it z equals, and then plot the 2 points, and then try and just sort of manipulate the zooming and rotating until you can make sense that this is a saddle point and that's a max. It's kind of nice to look at the maximum now. You know, it'll be that nice kind of bump, you know, like the top of that kind of mound sort of a thing. That is our very last example of the course. I think we ended on a good one. Go check out the homework. I'll see you in the live meeting.